I thought I'd make this short video about making use of the chemical shift tables that come with your textbook. Um, and this is something I kind of forgot to mention in the last video for starting your dry lab one, and I apologize for that. So uh, for those of you who have already, gotten started on like especially sketching the predicted NMR spectra and whatnot, like this is probably useful to you. But I'm sure you've seen the, elementary chemical shift tables you've seen in the OChem textbook or the ones that come in your OChem lab manual. Those are useful, when we are beginning, but this is really a lot more useful in actual practice. So I just wanted to go over that with you real quick. And I'd say the money that you're paying for the textbook, like half of the value I feel comes actually from these very well put together chemical shift tables. If you ever have to use NMR for any reason in your career at all, these are something definitely you can refer back to. So you should definitely keep this textbook with you if you think there's a chance you have to refer to anything NMR related in the future. But anyway, so let's say we have this compound here, and we want to sort of assign or I guess I should say predict what the chemical shifts would be for each proton. By the way, just so I don't forget to mention that in the carbon NMR chapter, I think it's 4, there's an equivalent appendix tables that have to do with carbon chemical shifts. These appendix tables are in the back of chapter 3, the proton NMR chapter. Okay, so let's say we want to figure out what the expected chemical shift of this methyl group would be. So what you do is in appendix A table, if you're looking for the shift of a methyl, you will look for this symbol. And if your methyl is attached to like another methylene or some sort of alkyl group, like this, right? Like just a simple alkyl group, then you would expect that methyl to show up somewhere around here. This shows like maybe 0.85 ppm or so. I think in practice, I expect this to be probably more like 0.9 ppm, but I guess I'm splitting hair at this point. So this is probably around 0.9 ppm based on that. And you notice with this chemical shift table, you can come up with a more precise prediction, which by the way, for the chemical NMR sketching assignment, I'm not requiring you to have like a really precise sketching. It just needs to be like in the right ballpark. Like I definitely do not expect your decimal point or decimal place to be accurate per se, but or precise. But anyway, and then what about this methylene here, right? Methylene CH2. So then I'll be looking for this symbol, methylene. And now this is attached to essentially regular alkyl carbons. It's attached to a carbon with fluorine, so keep in mind that in real life this could be shifted just a little more downfield, slightly than what we're gonna see, but that's a methylene that's attached to sort of a regular alkane, right? So you expect to see something like 1.2 according to that, but because at a distance there's an electron withdrawing group, it's probably going to be something like 1.4 in real life, but this still gives us a fairly precise ballpark. Now, what about this methine? Hopefully you recognize that as a methine CH group, right? So that is not only attached to like alkyl groups, but the most important group that it's attached to, of course, is fluorine, or I should say most influential group that it's attached to is fluorine. So you would look for that. Here's a methine attached to fluorine, right? So the chemical shift you would expect is somewhere around 4.8, okay? Right there in the table. What about this carbon? The most influential thing that it's attached to, directly attached to, is the phenyl group. Benzene, remember, is called a phenyl group. This is a methylene, so again, it's that like a white circle symbol, and that is next to phenyl. So where is that phenyl? Yeah, right here. Methylene attached to phenyl, so something like that. So you expect to see something like 2.6 ppm for that, for those protons. So that's how you would use this particular table. And then there's another one that's for the alkene or substituted ethylene table within this appendix. I didn't copy and paste that into here to show you how to use that one, but if you carefully read that page, I think you can figure out how to use it. One thing I might show, another different thing I might show you is this other table, which is appendix or chart D1, I suppose. And then this shows how you could predict like how what the chemical shifts might be on a benzene ring. This might require some explanation. So what this shows you is if the benzene is not substituted, if it's just a straight up benzene, the sort of the standard or default chemical shift you expect is 7.27, like right there. But if there's a substitution with these on it, of course the chemical shifts could shift. So this particular group, of course, is not listed here because it's very specific, but it's like that CH2 alkyl group that's attached. So the most closest, most similar thing is right here, ethyl group. And then you would predict all at ortho, meta, and para position, the shift you expect is around 7.18 or something like that right here. So that's the shift you expect. So likely, if you took the proton NMR of this, all these 5 protons probably are collapsing or overlapping around 7.18 ppm. Some of these are a little bit more interesting to think about. So for instance, the if you have bromine, okay, bromobenzene, let's say, at the oath position, you get the biggest influence because it's the closest to the bromine, right? So that chemical shift would be something like 7.5 ppm, whereas at the meta and para position, it would be like 7.22 or something. That's why the ortho and para and meta separated here. There's 2 different shifts that you expect for a monosubstituted benzene ring. Okay, so that's sort of how you typically read these. The most affected proton usually is the ortho. Now, one more thing I wanted to add is in this vicinity of these appendix tables and charts, you would see these schemes or charts with all these different sort of example alkenes and aromatic rings and different groups of compounds. And these tables are really useful because if you could use these as like sort of an approximation. Like if you have a functional group that's like, say, carbonyl conjugated to a double bond, you could use this to approximate like approximately what sort of chemical shift you should expect if you have a similar substructure in your compound that you're interested in predicting the chemical shift. So definitely make use of these chemical shift tables and charts. They should help you, and not just in this assignment, but pretty much all of the assignments in this class. So, okay, that's all. Thank you.